Chapter 7 is about linked list. Linked list. Let us suppose we have an array that contains the following 5 elements, 1, 2, 3, 4, 5, 6. We want to insert a new element with value 3 between 2 and 4 in the array. We cannot do so easily. We need to create another array that is long enough to store the current values and one more space for the 3. Then we need to copy these elements in the new space. This copy operation is inefficient. To remove this fixed length constraint, linked list is used. So linked list is not a fixed length, it's a dynamic length. Linked list is a list of items called nodes. What is it called? Nodes. All right. Nodes have two parts, value part and link part. Value part is used to store the data. The value part of the node can be either a basic data type, like an integer, or it can be some other data type, like an object of some class. The link part is a pointer, so we have a value and we have a pointer or reference, which is used to store the address of the next element in the list. So it's like a pair, a value, and a pointer to the next element. Types of linked lists. There are different types of linked lists. The main difference among them is how their nodes refer to each other. So what distinguishes the different types of linked list is how their nodes refer to each other. So we have singly linked, doubly linked, circular linked, and I think that's it. Let's go through them. Singly linked list. Each node except the last node has a pointer to the next node in a linked list. The link portion of a node contains the address of the next node. The link portion of the last node contains the value null. So this is the head, this is the linked list, which is a pair, value, and the pointer to the next. This is the value and the pointer to the next. There's a value to the pointer to the next. And at the very end, like this A3, it has a null, like it's the tail. So it has a head and a tail, all right? This is called singly linked list, a single. Doubly linked list, the node of this type has pointer to both previous and the next. So two pointers, to the first one and to the end. So the head starts with a null, previous, and the very last one doesn't point to any next one, which is the tail. So it ends with a null pointer as well. All right, null PTR. And this is the value and previous and next, previous and next, previous and next pointers. And this is called doubly because it has double pointers from both sides. Circular linked list. This type is similar to singly linked list, except that the last element have a pointer to the first node of the list. So it goes back, it's like a circle. It forms a circle. The very last one points to the very first one, forms a circular linked list. Circular linked list, all right? The link portion of the last node contains the address of the first node. Various parts of linked list. Head is the pointer that holds the address of the first node in the linked list. Nodes, items in the linked list are called nodes. They don't call them elements like arrays. They call them nodes. Values, the data that is stored in each node of the linked list is called a value. Link part of the node that is used to store the pointer of the other node. And in the doubly, we have two pointers, one for the previous and one for the next. We will use next and prev to store addresses of the next and previous nodes. Singly and linked list. And here's a description. All right. 0 element means empty linked list. 1 element means just a single node case and general case. The various basic operations that we can perform on linked list, many of these operations require list traversal. Insert an element. This operation is used to create a linked list. Print various elements. Search an element. Delete an element. Reverse a linked list. You cannot use head to traverse the linked list because if we use the head, then we lose the nodes of the list. We have to use another pointer variable of the same data type as the head. So the class is called linked list, and we have a struct called node, and the node has a value that has a pointer to the next, right? And a method, and a polymorphism, another method, right? And we have a pointer called a head, and we have an integer called list size, and the public methods are the size, smt, peak, add head, remove head, and the constructor of the linked list node. So we have the struct node, the node here. Size of a list, return list size. SMT function returns 1 if the size equals to 0, which means yes, it's empty. And return 0 if the size does not equal to 0. Insert element in linked list. An element can be inserted into linked list in various orders. Some of the example cases are mentioned below. Insertion of element at the start of the linked list. Insertion of element at the end of the linked list. Insertion of element at the nth position of the linked list. Insert element in sorted order in linked list. So we have no at the beginning, yeah, just like that. Insert element at the head, so we have add head. We say head equals to new node value on head and increase the list size by 1. So if we move up, this is add head, okay. All right. Let's look at the node function really quick. I'm gonna go back for a second. Okay, here we go. Value on node, so the value is this, the next is that, all right. Add head. All right. Insertion, we just saw that. Analysis, no, this is add tail. We just saw this add head and the analysis. We need to create a new node. This is a new node with the value passed to a function as argument, with the value passed to the function as argument. While creating the new node, the pointer stored in the head is passed as argument. The pointer is passed to the constructor, so that the next pointer will start pointing to the node or null, which is pointed by the head node. The newly created node will become head of the linked list because we added a head. Size of the list is increased by 1 in this step here. Insertion of an element at the end, and this is called add tail. And in this case, we create a pointer of type node and call it new node and equals to new node value ptr. We create another one called current and it equals to the head. If head equals to the null 0, it means there is no elements. Then the head equals to the new node. If not, while current next doesn't equal null pointer, current equals the next one. So we keep moving all the way to the end until we reach the current becomes the very last one, and then current next equal to the new, and here we added a tail. We added a tail when we reach this. All right. We make the current equals the new node. New node is created and the value is stored inside it. If the list is empty, next of new node is null. If the list is empty, then head will be stored. We'll store the pointer to the newly created node. If the list is not empty, then we traverse like move until the end of the list by using the next, using this while method. Finally, no node is added to the end of the list in this line here. This operation is inefficient, as each time you want to insert an element, you have to traverse, like move all the way sequentially to the end of the list. Therefore, the complexity creation of this list is insecure. So how to make it efficient? We have to keep track of the last element by keeping a tail pointer. Therefore, if it's required always to insert element at the end of the linked list, then we will keep track of the tail pointer as well also. Traversing linked list, print various elements of linked list, and we do this just before we use them. We compare with the null pointer. As long as it's not equal to the null pointer, then we print them all in the same line and keep going. Move, increase by 1, move to the next, and check again until we reach the end, then we exit. Analysis, we will store the pointer of the head in a temporary variable temp, and we'll traverse a list of printing content of a list and always incrementing the temp by pointing to the next node. All right. Complete code for list creation and printing the list. So linked list LL equals a linked list, add head, add another head, add another head, add another head, print them all. The methods are written above. We just went through them, and here's the main menu. A new instance of linked list is created. We call it LL. Various elements are added to list by calling addHead method. Finally, all contents of list is printed by calling the print method. All right. Sorted insert. Insert an element in a sorted order in a linked list given head pointer. So we'd like to insert the new value in a sorted order, like in the middle, right? So sorted insert. We create a pointer of the type node, and we do this by creating equals to the new node value and pointer. And then we make the current head, the current equals the head. If the current equals null pointer or current value is larger than a value. If it's the last one or it's larger. Then the next one equals the head. And the head equals the new node. While the next doesn't equal null pointer, and the current value of the next of the current value is less than the value. All right, then just go next, keep going further. And here the new node next equals to the current node next, and we start this next of the current inside this next of the new, and the new node will equal to the next of the current. Head of list is stored in current. No empty node linked list is created and initialized by sorting argument value into its value. Next of the node will point to the null. It checks if the list was empty or if the value stored in the first node is greater than the current level. Then this new created node will be added to the start of the list and handed to be modified. We iterate through the list to find the proper position to insert the node by using the while. Finally, the node will be added to the list at the proper position. Where do we stop? When we have this doesn't equal null and the value is smaller. Once it becomes equal or larger, we exit the while loop. So we point to the proper position in this while loop. Right? Finally, the node will be added to the list. Search element in a linked list. Search an element. We try to find an element. And here the function will be used is present. And if it's present, return true. If it's not present, then like the value equals the data, then return true. Otherwise, return false, like it's not present. So is it existing or not existing? That's all we need. All right. Search element in a linked list given a head of the pointer and value returns true if the value is found in the list, else returns false. Search in a single linked list can only be done in one direction. So we start from the beginning as long as it doesn't equal to the null pointer. Each time we increase, like the next, until we reach the null pointer, then it goes, finishes. It means the end of the linked list. All right. Since all elements in the list have pointer to the next item in the list, therefore traversal of the linked list is linear in nature. Traversal means shifting, like moving one by one. All right. Analysis: we create a temp variable which will point to the head of the list. and here's the temp variable. It's a pointer of type node construct, and it points to the head. Using a while loop, we will iterate through the list until we reach the end. The value of each value element in the list is compared with the value given using this if statement. And if the value is found, the function will return true. Says yes, it's present. If the value is not found, like all this iteration finished and all these are false, then we return false. If the value is not found, then false will be returned from the function in the end. And delete element from the linked list. If I want to delete an element, all right. Just like this, we delete the first element, then we make the head pointing to the A2 instead of A1, and that's it. In other words, we are deleting the first element in the linked list. Linked list remove head. So we have a function called remove head. We'll delete the very first element. We'll create a node called delete me and make it pointing to the head. The value equals the value of the head. The next equals to the head. All right. Decrease the size of the linked list by 1 and delete. First, we need to check if the list is already empty. If the list is already empty, then throw empty list exception. If the list is not empty, where did we check? We checked it here. If the list is not empty, then store the value of the head node in a temporary variable value. Store the address of the head inside delete me variable. We need to find the second element in the list and assign it as a head of the linked list. Since the first node is no longer part of the list, we need to free it. Decrease the size of the list and return the value stored in the temporary variable value. So when we delete it, we return its value. Delete node from the linked list given its value. If we have the value, we traverse through the linked list, and once it matches, we delete that. So we have this linked list, and we found the value, which is A3. Then we just connect A2 with A4, then delete the A3. Delete node by value, del value. All right. If the list is empty, then we return false from the function, which indicates that delete node method executed with error. And here's the empty with throw exception. If the node that we need to be deleted is head node, then head pointer needs to be modified and point to the next node. And a while loop will traverse the linked list and try to find the node that need to be deleted. We do the while from the beginning until the end. If this value of the next one equals the deleted value, what do we need to do? We need this next point to the delete me. This next in the term decrease this and call the delete me and return done. Like, yes, we deleted. We were able to find the value and deleted. So here it just returns from deleting the very first value. If we want to delete all the occurrence of a particular value, like we keep scanning, traversing through the linked list until we remove all items that contains that value. In this case, we don't, after we call delete me like before, we don't return. We just keep going through. We don't return. We just remove the return here and just keep going. So we'll delete everything that contains that value. Deleting a single linked list. Delete all elements in a single of a linked list. So we start propagating through them, and every time we go to the next and delete. And then at the end, the head equals the null PTR. So it's all elements are done. Traverse the list and delete all nodes one by one, then point head to null PTR. Like there's nothing. The size should be 0. Are we decreasing the size here? Oh yeah, the size should be 0. Traverse a singly linked list iteratively using 3 pointers. Reverse a linked list. Reverse a linked list, a single linked list, iteratively using 3 pointers. So we have a pointer called current and previous and next. And we start going, and the next will point to the next. The current will point to the previous, and the previous will point to the current. And the current will point to the next. This list is iterated next equal to the next node of the current. Make the current node next to the previous. Then iterate the list by making previous point to current and current point to the next. Recursively reverse a singly linked list. Recursively reverse a single linked list argument our current node and its next value. Arguments. Recursively reverse a singly linked list arguments our current node and its next value. And this is done using this piece of code. Reverse recurse function will call a reverse recurse util function to reverse the list and pointer returned by the reverse recurse util will be the head of the reversed list. Current node will point to the next, and previous node that is the previous node in the old list. A linked list can be reversed using 2 approaches. Well, one approach is by using 3 pointers. The second approach is using a recursion. Both are linear solution, but 3-pointer solution is more efficient. Why? Because the pointer doesn't copy the values, it just copies the address, and it's quicker. Remove duplicates from linked list. Remove duplicate values from linked list. The linked list is sorted, and it contains some duplicate values. You need to remove those duplicates, so it's sorted. You can create the required linked list using sorted insert. Linked list remove duplicates, so it propagates through the linked list or iterates. Once the value of the current equals the value of the next, then we delete the current. And we make the next points to the next. All right? Then we delete the delete me. All right? While loop is used to traverse a list whenever there is a node whose value is equal to the next node's value. That current node next will point to the next of the next, which will remove the next node from the list. Copy list reversed. Copy the content of the linked list in another linked list in reverse order. So we have two linked lists and copy this into that in a reverse order. If the original linked list contains 1, 2, 3, 4, the new list should contain the elements in 4, 3, 2, 1. And here's the code that does this. We have two lists, temp node 2, all right. I'm having a linked list called LL2 equals to the new linked list, and LL2 equals to the head equals to the temp node that we obtained from here. Traverse the list and add node's value to the new list. Since the list is traversing forward direction and each node's value is added to another list, so it formed list is traversing a given list. So this is in a forward. And just keep adding nodes. New node, and new node, and new node. So this will make it in reverse order. Copy the content of a given linked list into another linked list. Copy list. Head tell temp node current equals to the head. If current is null pointer, then LL2 equals to the null pointer, and that's it. Head node equals to the new node, tail equals to the new, and current, if the current, which is here, point to the next, doesn't equal null pointer, then create a new node, the next equals to the temp, the tail equals to the temp, and move to the next one, and at the beginning create a new one called LL2 that's equal to the new pointer that equals to the new linked list, and the head equals to the head. Traverse list and add the node's value to the new list, but this same time, this times always at the end of the list. Always at the end, add to the end. Because if you add to the beginning, it will be in reverse order. All right. Therefore, the firm list is same as the given list. Just copy, one by one. Compare list, compare to list given. So compare list, linked list pointer. Compare list. So this is recursive, it's calling itself here. And what's inside each one? If we have two. Okay, so this is like method overload or function overload. We have two. This takes just one, this takes two. All right. So if both are null, return true, both are empty. Else, the value of the first point refers to the second and last, and that's it. This is compared recursively. Moreover, if we reach the end of the list, then both lists are null, then both lists are equal, answer return true. Lists compared recursively if either one of the lists is empty or the value of the corresponding node is unequal, then the function will return false. Recursive calls compare list function to the next node of the current nodes. Finding a length of a given linked list. So we just use a counter and we propagate through the while and return the final count. So just knowing the length of a linked list needs to be done one by one. All right. Nth node from the beginning, just like that. And count is smaller than the index minus 1. And we keep moving to the next, then we return the value, and we obtain the nth node in our linked list. Nth node from the end is just like that. First, find the length of the list, then the nth node, you call defined length. Length minus n plus 1, nth node from the end. Equals to this from the beginning, okay? So from the beginning, we obtain it like this. Start index equal this, the size minus the nth plus 1. And here's an example. Loop detect, find if there is a loop in a linked list. So we have loop detect here, and we have another loop detect here. Find if there is a loop in a linked list. Hash table solution, traverse through the list. If the current node is not there in the hash table, then insert it to the hash table. If the current node is already in the hash table, then we have a loop. Loop detect, if we have to find if there is a loop in the linked list. Like this is a different approach. This is the first one to detect a loop. This is the second one. All right. There are two ways to find if there is a loop in a linked list. One way is called slow pointer and fast pointer approach. The other is called reverse list approach. Both approaches are linear in nature, but still SPFP, which is slow pointer, fast pointer approach, we do not require to modify the linked list, so it is preferred. So this is the preferred. Find if there is a loop in a linked list. If there is a loop, then return 1. If not, then return 0. Use slow pointer, fast pointer approach. Fast pointer, slow pointer. Find if there is a loop in the linked list. If there is a loop, then return true. If not, then return false. And here's the loop detect. Slow pointer, fast pointer. If they equal, then there we have a loop found. The list traverse with 2 pointers. One is slower pointer and the other is fast pointer. Slow pointer always moves 1 step. The fast pointer always moves 2 steps. If there is no loop, then control will come out of the loop. So return false. If there's a loop, then there come a point in the loop where the fast pointer will come and try to pass slow pointer. They will meet at a point. When this point arrives, we come to know that there is a loop in the list, so return true. Reverse list, loop detect. Find if there is a loop in the list, use reverse list approach like the other one. If the head equals the head, then we'll find. Store pointer at the head of the list and temp variable, and we do this by creating a no variable of a pointer of a node type, and we make it point to the head. Reverse the list, we call it reverse. Compare the reverse list and the pointer in the current list, head pointer. If the head of the reverse list and the original list are the same, then reverse the list back, the return true. If the head of the reversed list and the original list are not the same, then reverse list and back and return false, which means there is no loop. All right. Loop type detect. Find if there is a loop in a linked list. If there is no loop, then return 0. If there is a loop, then return 1. If the list is circular, then 2. Use slow pointer, fast pointer approach. All right. Remove a loop. Given there is a loop in a linked list, remove the loop. How do we remove the loop? All right. Loop through the list by 2 pointers, one fast, one slow. Fast pointer jumps 2 nodes at a time. Slow pointers jump one node at a time. All right. Fast pointer next. slope pointer just run next, right? The point where these two pointers intersect is the point of the loop. If that intersection point is head of the list, this is a circular list case, and you need to again traverse through the list and make the node before the head point to null. So we open the loop, we disconnect it, we make it like a line instead of a circle. In the other case, we need to use two pointers variable, one from the start and end. They both will meet at some point. You can mathematically prove it. Find intersection. Where do they meet? And in the next video, we'll talk about a doubly linked list.